So welcome back, everybody. And I'm wondering, do we have any announcements about homework that we want to make?
So nothing as of right now. So
Okay.
there are some code details that I'll answer on Piazza, but nothing to mention in class. Other than project proposals, I think most of the students here have submitted them.
Okay. Yes, I've spent a lot of time giving responses, so happy to continue the conversations. So we're going to pick up with the last bullet on this lecture that I began last time on the N-Body algorithm, and which is all about how to parallelize them. So last time was a rather math-heavy talk on how they all worked. And of course, I expect you to remember every last detail of the mathematics. Well, actually, just four lines will do. That's all we have to know is sort of the high-level structure, and that'll be good enough, I hope, to understand how to parallelize it. So both Barnes-Hutt and the fast multipole method have four phases, four sort of stages. And the math inside is different, but from a parallelization point of view, I hope this is enough. So we have to build a quadtree. I'll keep it all in 2 dimensions, just to keep it easier. Then you have to traverse the quadtree from the leaves to the root and build something called outer expansions. And in the case of Barnes-Hutt, that was simply the center of mass and the total of mass for each box, and you pass that up until up to the root. And what is that good for? If you know the mass and center of mass of one box, that's good for what's called an outer expansion. That tells you when you're outside the box, far away, it evaluates the gravitational force from everything inside the box. Okay, so we'll parallelize that. That's a tree traversal. There are lots of parallelism there. Then we have to traverse the quadtree from the root to the leaves. This is in particular for fast multipole, and build inner expansions. So remember, I'll remind you a little bit later, but an inner expansion is a formula, a Taylor expansion for the potential inside a box due to everybody who's far enough away, right? So the contributions of everybody else who's far enough away. And that is, I go from the root down to the leaves to do that. Another parallel tree traversal. And then that, when I'm done, will take care of everybody who's far enough away. And finally, I have to do direct N-body interactions with my nearest neighbors. Because it's not worth approximating the guys who are right next to you. We'll just do direct interactions with them, and they're not very many. So those are the things that I have to parallelize. And the point of describing it at this very high level, just with 4 lines, is that there's one parallelization scheme that will work for all of it. Of course, the details will vary between Barnes-Hutt and fast multipole. And in fact, this was put into a PhD thesis a number of years ago by a student here, David Blackston. And so I'm going to sort of use that as a way to explain, the parallelization scheme. So we have to, and in fact, he built an auto-tuner. Because there's so many different parameters and choices in the way you do the parallelization, he sort of built it into this system, and it could tune for doing the right kind of automatic parallelization. And that work has been continued by other people since then, and I'll talk about that too. So the first thing we have to do is make sure it's all well load balanced. So we're going to assign regions of space to each processor, and the processor will be responsible for just those particles inside there, and talking to whatever neighbors are necessary. And these regions are going to have, or they're not going to be squares, they're going to be other shapes because we have to get load balance. And there are several different interesting ways to choose different sizes of space. And, but when we're done, the whole point is that each of those regions should have about the same amount of work to do. So they should have about the same number of particles. There's different ways of doing the load balancing, but that's the easiest way to think about it. And so each processor then is going to store the leaves of the quadtree for the particles it owns. But it's going to spend a lot of time traversing the tree, right, to do all of the force computations. So it's not going to just store the leaves, it's going to store all the ancestors of the leaves that it owns, all the way up to the root, because it's going to keep going up and down that tree. So of course, the leaves at the top, like the root, everybody shares the root, and a few layers down, those are going to be shared by lots of processors. So we're going to replicate that data so that everybody can keep traversing it, because everybody's going to start at the root, and to not have any communication when we do all those independent tree traversals. So and this is a trick we've seen before in linear algebra. We're going to replicate the data to avoid communication. And this is an idea that's been around for a while here. And then when you do that tree traversal, you need not just to know everybody who's inside your nodes at the leaves, right? You need to know some of your neighbors' information too, right? So that you can get their expansions and evaluate them inside. So you need to know some neighboring parts of the tree. And there's a name for that. It's called the locally essential tree. Those are the parts of the quad tree that you need to own so that you can get all the information you need. And so there's going to be another phase of the algorithm where we replicate just sort of the boundary parts of the quadtree on each processor, kind of its ghost zones, a way to refer to it. And so whenever you do the tree traversal, you own all that stuff and you don't have to talk to your neighbors anymore. And that, as I said, that part of the tree that you need that your neighbors officially own is called the locally essential tree. So they're going to have to send that to you. And then once we build all this interesting data structure with bits of replication in it, then the force computations will be embarrassingly parallel. You'll own all the data that you need to evaluate it. So that's the game plan. And so let me go back up here to where we assign regions of space to each processor. Now, there are two ways that people have tried. And here's the simplest one that was tried first. And this was done in that first Gordon Bell Prize winning paper back in 1992. And it was called Orthogonal Recursive Bisection. And it's a pretty simple thing, so I'll just do it in 2 dimensions. So this is kind of a quad tree. So what I'm going to do is I'm going to divide left and right. I'm going to pick this blue line so that half the particles are on the left and half the particles are on the right. And I'll move it sideways as needed. And then once I've divided the particles in 2 equal halves, I'll pick the horizontal line. So I'll pick that red line and move it up and down until half the particles are above and half the particles are below. I should say a quarter of the particles are above and a quarter of the particles are below. And I'll choose a red line over here, but it may not, line up with that red line depending on the distribution of particles. But again, a quarter above, a quarter below. And I'll keep doing that recursively, and I'll get some sort of pattern that looks like that. And then each of and so in this case, I think I have 16 rectangles, each one of which has about the same number of particles, and I can assign those to 16 processors in principle. And that worked reasonably well in 2 dimensions, but it didn't scale so well to 3 dimensions in terms of how much communication was necessary in sharing. So here's the other scheme, which was called cost zones. And this dates back a while too. It was invented kind of twice, once for shared memory and once for distributed memory, and they had slightly different names for it, but it was the same idea, cost zones and hashed octrees. And we'll just use the name cost zones. So what we're going to do is build the quad tree, and here I've drawn it out in its tree form, and here I've drawn it out in its, graphically, so we can see what each node of the tree corresponds to each little light blue square in there. And what I'm going to do then is once I've built it as though everybody is populated, but of course if the particles are not uniformly distributed, I may not actually go down to the same level everywhere. But just for this picture, let me assume there's at least 1 particle in each of these little light blue boxes. So then what I can do is count the number of particles in each little light blue box, or get some sort of estimate of the total work. And so the total work, let's just say it's the number of particles. And so what I'm going to do then is start counting, go from left to right, and suppose I have 4 processors. And I'm going to say how much work is there, and I'm going to keep on going until I get a quarter of the work. And I'm going to assign that to the magenta processor. Then I'll keep on going until I get the next quarter of the work, the next quarter of the particles, and I'll assign that to the, what color is that? That's the green processor. And then the brown processor, so that it gets those, and then finally the orange or pink processor gets those. So what I need to do to make this work is choose some sort of ordering in which to go from left to right in this tree that corresponds in some geometric way to that. So the question is, how do I want to do that? I would like it to be the case that as I go from left to right here, I get locality, right? So that these blocks are close together. And this is an idea we used before, first in linear algebra. And what was the name of this ordering? So here, let's look at it. So first I get all of those, and then I start there and I get all of those. I'm sort of traversing the tree, the leaves recursively, and it's called a space filling curve. So if you remember that. So that means I do the southwest corner, then the southeast corner, then the northeast corner, then the northwest corner. And then inside each of those corners, I do it in the same way. I do it in this backward C form all the way down to the bottom. And so that means here, all these guys tend to be contiguous, so they all get assigned, but I need a few more to balance the load, so I'm going to grab those. And so it's not a perfectly contiguous bunch, but it's pretty close. And so that is going to be the scheme in which we assign the work. So how do I actually build that and assign it? So I need some sort of numbering scheme, so to go to sort of one more level of detail. And this is where the hash function comes in. So what I'm going to do is assign a number, an index to each of the leaves in the tree. So what I want to do, going back here, is assign a number there. He's the root, 1. And then I have 4 more leaves there, so they're going to be assigned some numbers. And that's almost legible, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And that'll give me the 4 leaves at the next level. And then each of those has 4 children, so I need 2 more bits to do that. So what I'm going to do then is assign a single integer. And where do those integers come from? Basically what I'll do is I'll take the x-coordinate of each of these, write it as a number with a bunch of bits in it. Take the y-coordinate of each of the center of each of these. That's another number with a bunch of bits in it. And I'll just interleave the bits. And so I'll take the x bit, y bit, x bit, y bit. And that gives me the key that uniquely identifies each particular vertex in that tree. So what do I do now once I've built that very simple unique index? Here it is again. This picture just repeats what I had before. What I'm going to do is just consecutively count through those particular numbers. So for example, I'm going to start with the purple processor. I ask, who do you get? So I'll start with 0, 0, 0, 0, 0, 1, 0, 0, 2. And that's going to give me that guy, and that guy. So this is actually not a backward C. This is an N-shaped Morton ordering. So the order in which I'm traversing it is an N, and then N recursively. So that's this particular interleaving that I happen to do. So I'll go, this is box 0, box 1, box 2. And at that point, I've got a quarter of the work. I assign that to the magenta processor. Then I get boxes 3, 4, 5, 6 to the green processor, 7, 8, 9, 10, and then everybody else goes to the last processor. And so that will do the guaranteed load balancing, and it will also, because it's a space filling curve, tend to give me all the locality that's possible. So that is the way we build the Quadtree and do the load balancing. Any questions? So there's a kind of a chicken and egg problem here, which is the whole point of this was to build a Quadtree in order to build these costs. So what I did was I wrote down the Quadtree, and then I used that to build those cost zones, those nice colored regions. And the whole point of that was to determine how to build a Quadtree, right? So I could balance the load across all the processors. So I sort of have a chicken and egg problem. I want to make it parallel to build a Quadtree, and that wasn't parallel there. I mean, it was a nice picture. So how do I build that without having, spending too much time to build it in the first place and then figure out what the optimal thing is? So if you're only going to build a Quadtree once, maybe you wouldn't care how much it cost. But in practice, right, you're going to have to update that Quadtree once in a while because the particles move. And so that may be perfectly good for a bunch of time steps, but every once in a while you're going to have to do the rebuilding, so we don't want it to cost that much. And it's a simple statistical sampling idea. What all the processors are going to do is take a small random subset of their particles, send them to one processor. Hopefully that will represent the distribution of particles perfectly well. And then that one processor will build this and decide which regions of space are assigned to each processor, just using a small statistical subset. And then hopefully that'll be good enough to balance the load. And then processor 1 broadcasts all the information about what this tree looks like to everybody else. And then the big work occurs. Each processor says, okay, I own these guys. Who should own them? Which processor should I send them to? Everybody exchanges particles as needed to get them to be assigned to these particular pictures. And then the rest of the algorithm can continue. So it's important that every processor know what this entire picture looks like, because remember, we're going to be replicating data. So the magenta processor is going to have to know whether, which data it gets from the green guy and which guy it gets from the brown guy. So everybody has to have this global picture. But we don't want to spend too much time to compute it. Okay, so now the next question is, how do I replicate appropriately parts of that tree on all the processors so that I, when I finally go repeatedly traverse the tree to compute the forces, it's all local information. So I just want to replicate the little bits of the tree. And so here are 2 ways that people have tried it in the past. And everybody tried it in shared memory first, obviously. Everything's done in shared memory first. And there, the idea was very simple. I mean, the cache will do it for you, right? You just touch the tree. The first time you touch it, it's going to have to go to somebody else's memory, and it'll bring it into your cache. And the next time you need it, it'll be there, right? This is what caches are supposed to do. And the trouble with that is that it worked for a while, but it didn't scale all that well because the cache memory just kept having to grow and grow as you tried to increase the number of processors. And so after a while, it ran out of scalability. And it wouldn't work on big distributed memory machines anyway. So then they moved to distributed memory. And in this case, instead of the the processor who needs the data going and reading it and the hardware automatically sending it to you, the guy who owns the data says, does this neighbor need it? I'll send him what he needs. Does this neighbor need it? I'll send him what he needs. So each processor has to look at its information and say, what do I have to send to who else? To which neighbors need it? And that's called a sender-driven protocol. So what we need to do is have each processor look at its subset of the quadtree that it owns and decide which subset has to be sent to whom. And so let me just tell you how that decision is made at a very high level. And it turns out here, Barnes-Hutt's actually a little more complicated than the fast multipole method. And because if you remember when I talked about Barnes-Hutt, the decision about which masses and centers of mass it could use was a little bit more complicated geometric decision, instead of just looking at the structure of the tree. So here's the general thing that happens in Barnes-Hutt. Suppose I have two processors, call them J and K, and N is a node, a leaf in the quadtree on processor J. And what processor J has to decide is, do I have to send that information, that mass and center of mass, over to processor K? So or does it not need it? So how does it decide? Remember, the mechanism that we use to decide it is, do you look like a little white dot in the sky, right? And so what was the metric of, do you look like a little white dot? What we did is we took the size of the node, node is a square, and D is the size of that, and we divided that by the distance to whoever's going to evaluate you, right? And so if that ratio is small, if you look like a little white dot, if that ratio is small enough, then I can use only the mass and center of mass of everything in that box, and that's all I need, right? So that's the mechanism I'm going to use. So what does processor J does, who owns node N in the tree? He says, well, how big are you? Here's the size. How far away is the nearest point that could be owned by processor K? It knows what the quadtree looks like, so if it knows where the nearest corner is, and it says, okay, let's suppose that's distance r, there could be somebody in that corner. And so I can compute that ratio d divided by r for node n. So then it has to decide, okay, I can compare it to that threshold theta, that's the user input, and decide what to do. So here are the two cases. Let's suppose that this particular node is small enough to use. Then I might want to send it. But if it's too small, I don't want to send it. I want the biggest box and just send the least amount of information. So this first criterion says, this node is small enough that I'm guaranteed that I can use it in the other processor for any particle that it happens to be there, but I can't use any of the parents. I can't use any bigger box. So if I look above the node to its parent, doesn't look enough like a white dot. So then I send it. But I also remember I need to traverse the whole tree, so I do need to send all the ancestors, all the parents. So the parent and the grandparent and so forth. So I also send it if it's too big, if I can't use it, if the ratio is too large. So I send the first guy that I can use and everybody else. And that means that node N is part of processor K's locally essential tree, and I collect all those nodes and I send them in one message. Okay, so for the fast multipole method, it's a little bit simpler, maybe. So I'm going to have that on the next slide. But are there any questions about Barnes-Hutt before I continue? So remember, in the case of the fast multipole method, all I had to do was look at the tree and sort of say, are you a cousin, but not a cousin who's living right next to me, right? That was the criterion. And so here are the pictures just to remind you of that discussion. So if I'm node N, then the question is, what information do I need from everybody else? And let me just remind you of that. So node N here is that little light blue square there. And so I need to do interactions with everybody who's not my immediate neighbor, so everybody who's not one of these white squares. So how am I going to do that? Well, what I'm going to do is I can go to my parent, who's exactly 4 times larger, there's the parent, and say, what can my parent tell me? Well, my parent has an inner expansion. My parent has a formula that tells me tells me the force for everybody inside the parent who's not an immediate neighbor, so that's basically all the red stuff. So I can grab that from my parent. So my parent is owned locally, so that's easy. There's no communication required. But then I also need all these smaller ones. These are too close for my parent to be able to help me, but they're far enough away that I can use the expansion of this stuff to figure out what's inside here. So I need the outer expansion of that interaction set to evaluate here. So this was the rule for deciding if this formula, mass and center of mass for Barnes-Hutt, a few more terms of the Taylor expansion for fast multipole, needs to be sent to node n. So we just sort of loop around here, and each processor can ask, am I an interaction node for somebody else? If so, I have to send my I block to the n block. Okay. So that is, and then that becomes the locally essential tree. And there's obviously a lot of bookkeeping that I'm skipping over, but that's the basic idea. So are there any questions? That's all there is to the algorithm of this most basic kind. So let me give you some data as to how well this scales. So I'm going to do some data that's, my goodness, 30 years old? No, 20 years old. And then some data that's a couple years old. So to see how things have been going since then. So this was the first Gordon Bell Prize, which was in 1992. And so this was a whopping 512 processor Intel Touchstone Delta, as they called it back then. And so this particular data is for an 8.8 million particle system. And let me tell you what happened first when the particles were uniformly distributed. So that's the easiest case. And since this was Barnes-Hutt, they weren't looking for a very small error, root mean square error. It was between 1% and 0.1%. And last time I told you that was sort of the average error in the forces per particle. The whole thing ran in 114 seconds, getting 5.8 gigaflops, like your laptop. But here's where the time went. So what I'd like to do is look through all these this breakdown of the time and ask how good are they, right? Did they waste a lot of time, in overhead, or are they close to as good as possible? So here are all the phases that were measured. They had to decompose the domain. That's the phase where everybody sends their information to one processor who builds the tree and figures out how it should be load balanced. That took 7 seconds. And then that processor had to send that structure to everybody else and actually build the quadtree and move all the particles to where they belonged. That was another 7 seconds. Then there was tree traversal. And so that was, building the expansions of the masses and center of masses and so forth. That was 33 seconds. And of those 33 seconds, 6 seconds were communication, and the rest, 27 seconds, was doing arithmetic of one sort or another. So let's say useful work. So finally, having built all that, we could evaluate the forces. So the really practical, useful work, if you like, evaluating the forces was 54 seconds. Now, how well was it load balanced? So one way to measure that is, what's the difference in time between the first processor that finished and the last processor that finished? And the answer was the last processor finished 7 seconds after the first processor. So if we had asked, what's the best we could have possibly done, maybe it would have been 54 minus 7. So maybe that would have been 47 seconds would have been the best that we could imagine doing, assuming that the force evaluations are running at reasonable speed. So how does 47 compare to 114? Well, we could have gone another 2.5 times faster if all the other overhead and load imbalance had disappeared. So, it's not terrible, a factor of 2.5 speed up. So you haven't it's not a complete waste. So, but how much benefit you could possibly get by speeding up all this other stuff. And what happens if we go to a non-uniform distribution, which I think is they put all the particles on the surface of a sphere or something like that. It went from 114 seconds to 160 seconds. So the load imbalance it becomes more problematic when it's a non-uniform distribution. So yeah, so that was the first set of results. So let me go to another set of results, which is on a Cray T3E. So, and this, I believe, is actually just, so this was an early highly parallel computer, and this was not Barnes-Hutt, it was fast multipole, and the goal was 10 to the minus fourth, which is much more challenging to get. So you can't do that with Barnes-Hutt so well. And so let me just give you an example of 50,000 particles running on one processor and 4 processors, just to see how well it did there. So to sort of tease apart the data, because some of the data, the story looks like the last slide. So let's see what we have here. So I'm going to do 2 cases, one where the particles are uniformly distributed and one where they're non-uniform, to see what the difference is. And I'll do it on one processor, and then I'll do it on 4 to see how much faster it goes. And so the tree, here's the size of the tree, the number of nodes, and fortunately it built the same tree, whether it was sequential or parallel. So 2,000 vertices or almost 6,000 vertices in the non-uniform case. The depth of the tree was this far, and here are the times. The time went from 172 seconds on one processor to 39 seconds on 4 processors, so the speed up was 4.4 on 4 processors. So does that seem like a mistake, like there was a bug, or does that seem like not, I mean, good news, but possible good, but true good news? So where could we get? How could we get this is called a superlinear speedup? It's bigger than p. So anybody want to venture a guess as to how I could get a 4.4x speedup on 4 processors? So what do when I increase the number of processors, what extra resources do I get besides hardware resources do I get besides processors? Memory, exactly. I have 4 times as much cache. And so that means a lot more of this work can be done on stuff that's stored in cache, and so that's where this extra speedup is coming from. And so that is a good thing, and you should look forward to that when it happens to you too. It's not guaranteed by any manner of means. And in the non-uniform case, in fact, there was a 6x speedup by having this extra cache memory available. But maybe the real speedup is how much faster did we go than the naive n-squared code, and indeed the speedup is enormous, as it should be, so factors of 50 or 500. So this is these are both old examples, but this is the sort of thing actually I want you to do in your final project. So I'm sort of walking through this data to give you an example of when you get your data on your final project and you break it down into pieces and you plot the time of all the parts as a function of the number of processors and how much memory. You're going to have to ask yourself, does this make sense? Is there a bottleneck I didn't expect? Is there a speed up I don't understand? And sort of do this kind of mental analysis to interpret your results. So let's go from 1999 up to 2010 and show you some more recent results on attempting to tune this. And this is was a joint paper by a bunch of folks, some of whom are local, and one of whom, Richard Vudock, used to be local as a graduate student before he became a professor at Georgia Tech. And so this was work presented at IP-DPS 2010. And this is going to actually extend the fast multipole method in a very interesting way to an algorithm I alluded to before called the kernel-independent fast multipole. So it works not just for inverse square laws, it works for basically any smooth potential function. So I'll get to that on the next slide. So here is going to be a study of a whole bunch of different tuning parameters, many of which will look familiar from assignment 1, lots of low-level parameters in addition to high-level parameters, where they tried different data structures. They tried different SIMD instructions. They tried multi-threading. It turns out that if your goal is only to get maybe 6 digits, then you don't need to run in double precision. You don't even need to run entirely in single precision. It turns out there's some special instructions in these platforms which are less than single, and they got enormous speedups by using those. I'll tell you about that in more detail. And various other kinds of tuning. So here are some of the speedups that they got. So on a 16-thread Intel Nehalem, they got a 25x speedup. Again, one of those superlinear ones by doing a good job compared to the naive code and taking advantage of all that extra cache memory. So 9.4x on this 8-thread Barcelona. And if you remember the Sun Victoria Falls, I talked about that machine when we were doing sparse matrix vector multiply. That only has a limited number of cores, but it can have as many as 8 hardware threads per core and shift between them automatically. It does chip multi-threading. And so it can have as many as 128 threads ready to run. And if one of them is waiting for memory, then it'll just, in the next cycle, it'll take one of the other threads and run them. So in principle, if everything is perfect, you can get 128 speed up, but it got 38, which is reasonable. So the other thing, and I'll have this in another slide, is they also implemented this in a GPU. And to their sort of surprise, they couldn't do a whole lot better in a GPU. But I'll explain why when I get to that slide. So the other thing that this algorithm did, which grew the tuning space, is they used something called the kernel-independent fast multipole method. And as I said before, it's a way to organize this so that it works not just for inverse square, but for anything that's sufficiently smooth. So here is the way to do it. Imagine instead of a square, you have a circle, and you want to have you want to have some circle with a lot of particles in it, And you'd like to have a simple formula that if you're far away, an outer expansion, so if you're far away from that circle, you have a simple way to evaluate the potential due to any particle in there. So here's the idea. What I'm going to do is replace all the particles in the circle by evenly spaced points on the circumference of the circle. What I need to do is pick the mass, let's say, of each of those points on the circle so that if I'm far enough away, it looks like the same thing. So in other words, I take all the particles inside, I replace them by evenly spaced ones on the circle, a small number of them, and if I'm far enough away, the potential that I feel because of the points on the circle feels very close to all the larger number of particles inside the circle. And so it's an interpolation problem, right? I need to sort of do interpolation along a circle. And all it needs to do that is a formula which says if I have a mass at this location, I can evaluate the potential at that location. All it needs is a black box formula supplied by the user. It can be any potential you want. You know, Stokes flow, modified Laplacian. So that's why it's really a black box thing. So what I need to do, it spends a lot of its time doing interpolation on a circle. And if you have evenly spaced points along a circle, you shouldn't be surprised that the fast Fourier transform comes up. So it spends a lot of time doing arithmetic with a fast Fourier transform. And that is something that people have worked very hard at tuning. And we'll have a whole lecture on that later. But let's just say they use a package which lets you tune fast Fourier transforms. So that's part of their tuning space too. And so that's part of the algorithm innovation here. The next thing is they also did a lot of low-level tuning, the kind of stuff that you folks tried in assignment 1. So there's all that SIMD instruction set that I talked about that was particular for the x86 architecture. So here's the new instruction that I mentioned that's less than single precision. Because remember, they're not trying to get single precision. You know, they're happy to get 4 digits of accuracy in the output. And if you're doing the inverse square law, then you spend a lot of time computing 1 over the square root of a distance. And so the question is, you know, can I do that cheaply? And it turns out this machine and other machines have a special instruction for doing that. It's called the reciprocal square root approximate instruction. And what it does is it gives you to 12 bits. So single precision would be 24. So to half precision, to 12 bits, it gives you 1 over the square root of your argument. So why is it in this machine? It's because, well, what if you wanted to compute the actual square root? Well, if somebody hands you the reciprocal square root, one step of Newton's method will double the number of bits. And it'll give you all 24. And that's enough to get the actual square root. But if you only need 12 bits, you just stop right there to get 1 over the square root of r. And so that's one of those little hidden things in some of these architectures. And so they use that. They also played with different data structures. So structure, SOA is short for structure of arrays. You can also have array of structures. It's kind of like transposing your data structure. And some of those let you use SIMD instructions better than others. So they played with all those possibilities. You may remember in fast multipole, it spends a lot of time doing matrix vector multiply to convert expansions around one point to expansions around another point. But the matrix entries are all known ahead of time. So what they did was they said, well, let's not actually write down that matrix. Let's do it in a sort of a matrix-free fashion, because a lot of those entries have, you know, algebraic relationships with one another. I don't have to store them all explicitly. And so they played with that and got speedups. And then there's tuning the FFT using this package called FFTW that I'll have a lecture on later. That stands for the fastest Fourier transform in the West. And as I said, I'll have a lecture on that later. And then they used OpenMP. This was all multi-core kind of stuff. And the last tuning parameter they played with was you build the quadtree, and at some point you stop when there are a certain number of particles in each box. That was Q. So that's yet another tuning parameter. Okay, so let me tell you how all this affected a single core performance, and then I'll do the multi-core performance. So this was single core optimizations, and this is all running in double, but they don't need double. I mean, but you know, the final output was less, and it's not uniform distribution. So all the particles are sitting on the surface of an ellipsoid, so that's a very non-uniform distribution, and all of these are different phases of the algorithm. And I'm not going to try to explain it. Let's just say because of the kernel independent stuff, there's a lot more traversing and building of data structures. And so it's just broken down this way. And the vertical axis is speed up. So 0% means it's the same as the naive code. 100% means you're twice as fast as the naive code. 200% means you're 3 times as fast as the naive code. And the colored bars say which optimization contributed how much. So for example, when you're going up the tree the first time, then doing this SIMDization, that got you 40% speed up. Using the Newton-Raphson approximation, using that special instruction for 1 over the square root of r, that gave you a big speed up. And then there's fiddling around with transposing your data structures, that gave you the green speed up. And then there's getting rid of the matrix to do the explicit conversions of expansions and being more clever about how to compute that, and that gave you the blues. And the place where you did all of the FFTs was just in this middle phase here. And doing FFTW instead of a naive Fourier transform also gave you a big speed up. So this was sort of the what happened on a single processor, and it gave you some parts of it sped up by factors of 4 and 5. So we still have to do the parallel part. So here's what happened when they tuned the parameter q, which is how many particles are in the leaves of the quadtree when you build them. And so what this is showing is, as a function of q, as a function of that tuning parameter, how long did it take? So down is good. And there are 3 different algorithms here. There's the reference serial code, which is the naive untuned code. And then there's the optimized serial code, the code I showed you in the previous slide. And then there's the parallel code, which is fully optimized. And so here you can see that if I pick 100 particles per node at the leaves, then that is the best I can do. It takes 168 seconds, and then it gets a lot slower. If I take the tuned code, it's a little less sensitive, but it's still 100. And if I go all the way to having the optimized parallel code, then the optimum is right there, and it's best to have 250 particles per box. And so that's why it's a tuning parameter. And the scale is not very good, but that is significantly faster than that. It's all very close to 0. And I get down to 10.4 seconds. So that's just an example of the tuning of the particles per box. And so finally, here is all the data in parallel for all the different platforms with all the different optimizations. And so here is the uniform distribution data. Here's the non-uniform distribution data. It's comparing an Intel Nehalem to the AMD Barcelona, to the Sun Victoria Falls, to having 1 GPU connected to an Intel Xeon, to having 2 GPUs connected to an Intel Xeon. And the vertical axis is performance relative to 1 Nehalem. And so this guy right there is always 1, and you'd like to be up above that. That's how many times faster you go. And it's on a log scale, so there are big speed ups here. So if I take a Nehalem and run on 1 processor, I run at speed 1. Then if I optimize it, doing all the sequential optimizations, I'm running at speed about 8. If I throw in OpenMP and do all those, do it in parallel and optimize the parallelism, I'm going at about 20 times faster. And then, what's the green stuff at the top? The green stuff says, well, let me ignore building the quadtree. Let me assume I'm just going to build that once and reuse it for a bunch of steps, which is, applicable for some, which is the right thing to do for some applications, not all. That gets me up to the top of the green bar, which is 55 times faster. Okay? And so here's the same story. But it only gets me up to 29 times faster, so the AMD isn't doing quite as well. It's about as good for 1 processor, but speeding it all up isn't that much faster. The Sun Victoria Falls, starts off, 10 times slower, but ends up 3 times faster. Even though it has 128 cores, each individual 128 threads, it's just intrinsically not that fast. So here's the embarrassing part. It's not faster to use a GPU. So it turns out that when they tried to tune it, they initially thought about, how do I do all these tree traversals on a GPU? That was just too irregular. And so what they do in this implementation is they do all the irregular stuff, all the traversing the tree up and down. They do that on the CPU. And then they only use the GPU for actually evaluating the forces. So all the data gets transferred there, and all that happens in parallel. And 1 GPU is not faster than doing it on the Nehalem over there. So it's a factor of 32. But if I do 2 GPUs, then I get to a factor of 60. It's a little bit better. And it's a similar story for the non-uniform case. So if you do, so this is a warning for those of you, or advice for those of you who are doing a GPU final project, that what work you assign to the CPU and the GPU is a tuning parameter, right? You probably don't want to necessarily assign the irregular stuff to the GPU. And when I gave, you may remember when I gave the dense linear algebra lecture, one of the examples I gave was Gaussian elimination, which you think is pretty regular, but still, the GPU only did a subset of it to make it run fast. Some of the irregular stuff, like factoring a tall, skinny panel, that was done in the CPU. That was a faster thing to do. So here it happens as well. So are there any questions? This sort of ends the story of all the data and speedups for N-Body. And people are still working on it quite actively. And you can see there's a lot of complexity in the algorithms, but which as I said, got the 2 inventors into 4 national academies. So it's well worth investing that much time in this very important algorithm. So I'm going to change topics now. I'm still going to talk about N-Body. And I'm going to ask, can we prove anything about how little I have to communicate in order to implement any of these algorithms? And so let me talk about the hierarchical case first. And all the the motivation for these hierarchical methods was to go from n squared to order n, or n log n. And obviously doing that much less arithmetic is a big win, and it's also good for reducing communication. But there were also lots of other tricks that people did, the locally essential trees. The data was replicated, so you only had to go across to your neighbors once, and then you did all the tree traversals locally. But coming up with a lower bound is an open question. It's a very hard question to formulate. Is there a minimum amount that you have to communicate? And one of the reasons is that these are approximate algorithms, right? So how many, you were willing to settle for, lower accuracy by definition, since they're hierarchical. So, does your lower bound may depend in some very complicated way on the desired accuracy. So this is an open problem, and I don't really have anything to say about it. On the other hand, I think we know everything there is to know about lower bounds and optimal algorithms for the direct methods. And where you do all n squared, or not necessarily even n squared, because remember for your second homework assignment, you did the direct N-Body algorithm, but you only did it within a cutoff region, right? So you only did it for particles who were close enough. You computed all the interactions there, and in fact, the fast multipole method has to do that too. It does direct interactions with the nearest neighbors. And so I'm talking about algorithms like that, where for some subset of the particles you have to, that are close enough by some definition, you do all, all pairwise interactions. So the question is, if that is your goal, if that's what your algorithm is there a lower bound on how much communication is necessary to do it, and can we attain it? And this theorem says the answer is yes, there's a lower bound, and yes, we can attain it. So here's what it says. So suppose I have p processors, and I'll keep it simple first. I'll say all interactions. And so that means I'm going to do n squared interactions. And each processor has some local memory. And if you remember when I did linear algebra, the lower bound depended on how much memory you had. So capital M will be the amount of memory I have in each processor. And let's suppose it's load balanced. I have to assume that, otherwise one processor could do all the work with no communication. That's not very interesting. So everybody's going to do an equal share of the work. Then the question is, how much data movement do I have to copy back and forth between the processors in order to compute all those n squared interactions? And here's the answer. It's lower bounded by a constant multiple. That's what big omega means. The amount of work each processor does, if they're n squared interactions and it's load balanced, that means n squared over p is the work each processor does, divided by its local memory size. So this is not quite the same formula, but it's very similar to the formula for linear algebra. For linear algebra, the numerator was, again, the amount of work, but that was n cubed over p. And the denominator was not m, it was m to the 1/2. But it was m to some power. That's not an accident. We'll see that in a moment. And so that is going to be our goal. And what about the number of messages? So the fewest number of messages I could send is send all this data packed into messages that are as large as possible. How big can a message be? The whole memory. So in other words, this is just a factor of m smaller than that. And that seems like asking a lot, to be able to send just all the messages are of maximum size, but that's the lower bound, and we will attain it. Okay. So as I said, if I'm not doing all n squared interactions, if I'm doing, you have a cutoff region or something like that, it's the same theorem. All I have to do is replace n squared, the number of interactions, with the actual number of interactions, whatever that is, some small fraction of n squared. It's the same lower bound. So the question is, how do I attain this? So let me tell you about the sort of naive algorithm and we'll see what happens there, and then we'll see how much better we can do. So here is the sort of naive way to do it, which, where I use as little memory as possible. So each of those little black dots is a particle, and I have p processors. And let me assume that each processor owns an equal number of them, so everybody owns n over p particles. And let me assume I only have enough memory to store that, or maybe 2 copies or 3 copies, but some small multiple. So what is the algorithm? And we've seen this before. I talked about it earlier in the semester. So first of all, every particle does all the pairwise interactions of the guys it owns, so no communication. Then each processor packs up all the particles it owns and sends them to its neighbor. And then this processor takes all of its particles, all of its neighbors, and computes all pairwise interactions. As soon as it's finished, it takes those particles it just got, sends them to that neighbor, then to that neighbor, then to that neighbor, right? So it's perfectly natural. Everybody moves in the circle. Every patch of particles visits each processor exactly once. So what is the cost here? The computation is perfectly load balanced. Everybody's doing 1/5 of the n squared work. So what's the communication bandwidth? Well, all of these n over p particles have to be moved to that neighbor, then to that neighbor, then to that neighbor, then to that neighbor. They have to move p times. So the total bandwidth cost is n over p, it's n over p times p, and that is equal to n. So now, let's ask, does that attain the lower bound? Well, what's the lower bound? The lower bound was n squared over p divided by the local memory. And if the local memory is n over p, it works out, right? This cancels exactly, and this very naive algorithm attains the bandwidth lower bound. And how many messages did I send? Well, I had to send, each guy was sent once, so there's p messages, and that also attains the lower bound. If I take n over p, square it, divide it into the numerator, it's p messages. So the naive algorithm does just fine. And so the question is, can we do better? The point is, the theorem is true not just for using the least amount of memory, it's true even if you have more memory. So, and if I increase m, these lower bounds are going to get smaller and smaller. So I have the potential to go faster. And the question is, can we do it? Well, yes. So here is the general algorithm. And we're going to call it 1.5D N-Body. So when we did linear algebra, we talked about 2-dimensional matrix multiply. And I said, oh, there's this thing called 2.5-dimensional matrix multiply, where we replicated the data and went a lot faster. We got 10x speedups there. Well, here it's going to be a very similar idea. I'm going to assume I have enough memory to replicate the data, and I'm going to get a big speedup. So let's suppose I have enough memory, not just for 1 copy of the data, but for c copies of the data. And so let me see what I can do with that. So let me assume that all my n particles are originally laid out on p over c processors. So that means how many guys are in there? It's n over p times c. So I'm using all the available memory. So now what I'm going to do is replicate it. So let's, in this case, c equals 4. So I'm going to divide the processors into 4 groups, and I'm going to replicate these copies of the particles on each layer. So now each layer owns a copy of all the particles. And the plan is that each of these c layers is going to do 1/6 of the classical algorithm. And when I'm done with that, each layer will have 1/6 of all the partial sums that I need to add up to get the actual forces. And when I'm done, I'll do this in more detail in a moment, I'll just do a reduction and all the forces will end up in the right places. They'll all be accumulated. And it's going to hit the new lower bound. Okay, so let me just do it step by step. I've divided my processors into C groups, and I replicate it. Okay, so everybody, this guy is copied, and it goes down there, so everybody gets a copy of that. And so now what I want to do is do a disjoint set of interactions on each layer. So here's the trick. What I'm going to do on each layer is send my particles to a neighbor so they can do the interactions. In the first layer, I'll send it to my nearest neighbor. The next layer, I'll send it 2 over. The next layer, I'll send it 3 over, and so on and so forth. And now, and this guy, I won't repeat it, so this guy will also move over 1, 2, 3. So this is just going to repeat for every column. I've just drawn what the first column is doing. So now everybody can do the interactions between their particles that they got and the ones that they already own. That's a disjoint set in all of these because I shifted it in a different distance. So now I'm just going to keep doing that p over c squared steps. So I'm just going to keep moving over a different distance on every layer. And I won't do all the algebra, but everybody is doing a disjoint set. Everybody's doing 1/4 of the sums, a different disjoint 1/4 of the sums. And so when I'm done, all of these, all the force arrays in each processor will own 1/4 of the contributions. And the very last step is I do a sum. All these guys get summed up to give me the total forces right there. Okay? So, and this turns out to attain the lower bound. So let me just tell you remind you what the lower bound is. So this is just repeating the algorithm. So the main algorithm is that at each step, I'm going to move something over 1. And so it's going to copy not n over p particles, but n times c over p particles. And so the overall, and that's how many steps it takes. So the latency is going to be p over c squared, that's the number of messages, and that indeed hits the lower bound. And the bandwidth is going to be n over c. It used to be n. Now it's a factor of c smaller. And that's a factor of c squared smaller than it was before. So if I can afford to have 2 copies of the data, the bandwidth is cut in half, and the latency is cut in 1/4. So I can get significant reduction. So this can keep going, right? I can keep making c bigger and bigger. Can I make it bigger forever? There's got to be a limit here. So what do you think the limit's going to be? It's when the number, how small can the latency go before it's obviously not attainable? Right, I mean, I can't send less than 1 message, right? So when this lower bound hits 1, I'm done. In other words, when c equals the square root of p. So there is sort of the limit. This is going to minimize communication. If I can afford to have the square root of p copies of all the data, then this is what my processor layout will look like. It'll be square root of p by square root of p, and each layer will do the right thing. This was actually published in 1995, this special case. But it turns out that it works in general. No matter how much memory you have, you can get this benefit. So let me show you some speedups, and they're pretty large. So here's some examples where on an IBM-BG, 8,000 cores and 32,000 particles. It seems like a waste, right? That's only 4 particles per core. You'd think that that's not you are going to be overwhelmed by communication. And indeed, if you use the naive algorithm, we are. But if you use the algorithm that I just showed you, the communication goes away entirely, and you get perfect speedup. So here, the horizontal axis is how many copies of the data I have. 1 copy, 2 copies, 4 copies, 8 copies. The vertical axis is time, so down is good. And it's color-coded by green is communication and red is arithmetic. And so if I just, and let's ignore the first column for a moment. So if I just use the usual, this is a 3D torus network. And so if I just have 1 copy of the data, the green is many times the cost of the arithmetic, and it's all communication. If I double the number of copies, that means I can certainly, if I can afford to have 4 copies, 4 particles, and I have 2 copies, that means I only have 8 particles per core. That's not very much memory. The communication drops significantly, 4 copies, and by the time I get to 16, you can't even see the communication anymore. This means I'm getting perfect speed up. Okay? And then overall, if I compare that speed to that speed, it's about 12x speed up overall doing this. So this is a good idea. So what about this? So it turns out that this particular platform, which they don't build anymore, had 2 different kinds of interconnect networks. It had a regular old torus, a 3-dimensional torus, connecting neighboring processors, but it had a separate tree interconnect, which was built especially for doing reductions and broadcasts. It was separate. And if you use that to do the reductions and broadcasts in the algorithm, the speed up was still there, but it wasn't as big as it was before. So it turns out they abandoned that extra network for the next generation of this machine. For BGQ, they threw it away, and they only have a 5-dimensional torus instead of a 3-dimensional torus. So that bar has gone away. So anyway, so that is how much faster we can make N-Body go. So we've seen this idea twice now, both for matrix multiply and linear algebra and for this N-Body stuff. There's sort of a natural algorithm where I have 1 copy of the data, and there are lower bounds, and we could attain them. And then, by replicating the data, and being clever about how you organize the work, I could decrease the amount of communication proportional to either m or m to the 1/2 and go a lot faster. So the question is, how general is that? So is it just N-Body and matrix multiply, or is it much more general? Well, I think you'll know the answer. So let me review matrix multiply and N-Body in this new notation, and then sort of generalize it to arbitrary code for which we can do this kind of stuff. So here is the naive matrix multiply, so I have a starting point. 3 nested loops, I, j, k, and there's the inner loop. And what we learned a long time ago, and you used in assignment 1, is here's how you optimize it to minimize communication. I'm just going to block it. I'm going to break my matrices up into blocks of size b. So I'm going to have 3 outer loops over blocks. The inner loops are going to just do a matrix multiply of these b by b blocks. And I want these to fit in cache. So these 3 inner loops are b by b matrix multiply. And the theorem that we talked about long ago, I didn't prove it, was that if I pick these blocks so big that all 3 blocks just fit in cache, so that means that b should be square root of the cache size by square root of the cache size, then this attains the lower bound, right? I'm going to read in these 3 b by b blocks, do all this arithmetic with no more memory traffic, and then write out the answer. And if I count everything carefully, the number of words moved between fast memory of size m and slow memory is the amount of work n cubed divided by the square root m to the 1/2. So the question is, where do these 1/2s come from? Is there some general theory that tells us that's a half and that's a half? So let me just restate this result in a different language, which is sort of to illustrate what the general theorem is. So there's the same code, the same 3 nested loops. And it turns out that all I need to know about this algorithm in order to optimize it, I can encode in this little 3 by 3 matrix. So this matrix simply tells me which arrays have which subscripts. So there's 1 column for each loop index, ijk, ijk. There's 1 row for each array, abc, abc. And there's a 1 to say which array has which subscript. So A, for example, has subscripts I and k. So there's a 1 there and a 1 there, but j is not a subscript, so it's a 0. So this delta matrix tells me everything I need to know about that code, just sort of recording it. So the next thing the theory tells you is to solve a little 3 by 3 linear program with this matrix. So what's a linear program? A linear program says, please try to maximize some linear combination of these 3 variables. So xi, xj, and xk are 3 unknowns, subject to some linear constraints. And the linear constraints are this matrix times that vector of 3 unknowns is less than or equal to 1, component by component. And so I'm just saying what the theory says, not why it's true. I'll get to that. So what's the answer when you solve this linear program? These 3 values of x's are 1/2, 1/2, 1/2. And their sum, which is what I was trying to maximize, is 3 halves. And let me call that magic number s. So let's suppose we've done all that. What does the general theory say? It says that no matter how you reorganize matrix multiply, then not just by blocking, any way you can imagine, then the number of words moved is going to be lower bounded by the number of loop iterations, n cubed, divided by the cache size to the exponent s that came out of the linear program minus 1. So that's 3 halves minus 1, or a half. And how do you attain it? Well, you're going to have to block the loops. And the question is, what are the block sizes? That's the big unknown. And the size, so I need to have a block size for I, a block size for j, a block size for k. And there they are. M to the xi is the block size for I, that's m to the 1/2. M to the xj is the block size for j, m to the 1/2, and so forth. So this theorem is true for pretty much any code. I'm just trying to illustrate it here. So now let me apply the same theorem to N-Body and see what and just illustrate. And I'll state the theorem in its generality. I just want to give some special cases first to illustrate it. So here's the simplest way to write down N-Body. I'm going to loop over all pairs of particles. So I equals 1 to n and j equals 1 to n. And what am I going to do in the inner loop? I'll take particle I and particle j. So that's an array where each array entry has a position and a mass. It can have a bunch of stuff. That's okay. And I do evaluate some formula, inverse squared, doesn't matter. And I increment the force on particle I. Okay? So it doesn't really matter what all that code looks like. All it matters is that I'm accessing location I of that array, location j of that array, and location I of that array. So everything I need to know to optimize that code, I can embed in this simple little 0, 1 matrix. There's one column for each loop index, I and j. There's one row for each array, so index. So pi is one index, pj is a different array, a different access, and then f, right? And so f is subscripted by I, pi is subscripted by I, and pj is subscripted by j. And so the rest of it is exactly the same. The theorem says, please solve this little linear program. It's the same linear program as before. Please maximize the sum of these two scalars, xi and xj, subject to the constraint that delta times x is less than or equal to 1. What is the answer to this very simple linear program? It's 1, 1. And the sum of the ones is 2. That's the magic number s. And so the theorem says that the number of words moved, no matter how you organize the N-Body algorithm, is going to be the number of loop iterations, which is n squared, to the power m to the solution of the linear program minus 1. So that's n squared over m. And what are the optimal block sizes? It's going to be m to the 1 by m to the 1. And that is exactly the algorithm that we used before, sort of in disguise. So now, just for the sake of showing you how general this is, let me apply it to some random code I wrote down. Yes, question. Do you have a microphone? Or is it a short question?
Does the theorem say you can only attain with those block sizes?
So the question is, does the theorem say you can only attain with those block sizes? So I think there are, no, because as we know from matrix multiply, there's other kind of recursive divide and conquer ways to do it. The question here, is there at least one way to attain the optimum for some arbitrary code when it's not already well known that there's many ways? So let me give you one example where it's by no means obvious that there is a lower bound or that there's a way to do it. And I kind of wrote down this code at random. So I just wrote down 6 nested loops. I just made them up. This does not implement anything anybody I know cares about. And I have 6 arrays, A1, A2, A3, A4, A5, A6. And I just pick random subscripts. So A1 is indexed by A1, I1, I3, and I6. And A2 is subscripted by those. And it's some big mess, right? As many lines of code as you want. But everything I need to know to optimize this and prove a lower bound is recorded in this matrix of zeros and ones. There's one column, just as before, for every loop index, so I1 through I6, so there's 6 columns. There's a bunch of arrays, and some of them appear more than one, so A3 appears there and A3 appears there. So every time it appears with a different set of subscripts, I just put a row in the matrix, and the ones and zeros tell me where who has which subscript. And so I want to know, can I optimize this? Is there some lower bound, and can I attain it? And so the theorem says, please write down and solve the same linear program as before. So now I'm going to have blocks. I'm going to have x1, x2, x3, one x for each of the columns. Please maximize their sum subject to the same constraints, that delta times x is less than or equal to 1. And the result is this bunch of random numbers, whatever they are. And their sum is 15/7, and that's that magic number s as before. So what the theorem says is that no matter how you reorganize this weird program, the number of words moved is going to be bounded below by the number of loop iterations, which happens to be n to the 6th, divided by m to the output of the linear program minus 1, which happens to be 8/7. And are there block sizes that attain it? Yes. You just use these guys as superscripts on m. So I1 is blocked by m to the 2/7, I2 is blocked by m to the 3/7, and so forth. And that gives you what the lower bound is. So these are just 3 examples. I now want to kind of give you a hint of what the general result is, because the general result actually applies to even more general code. I was just trying to give examples where I could write down the details. Okay, so here's the general way to think about it. So there was matrix multiply again. And everything I need to know about that is that I have 3 loop indices, and they're, I'm iterating over some subset of triples of integers, so Z3 are triples of integers. And it actually doesn't have to be a cube, right? It could be any arbitrary sparse subset. So this theory applies to sparse linear algebra as well as dense. As well as dense, it doesn't matter. And all I need to know is that I'm accessing locations subscripted by these, these things in here, ij, ij, ik, ik, kj, kj. So what's the general case? So this is the example I had before. I have a whole bunch of indices, and they're all looping over something or other. And I have a bunch of arrays. I can have as many arrays as I like. Here I have A, B, C, you choose. And the subscripts can be arbitrary linear combinations of the variables. So I can have I1 plus 2I3 minus I7. You know, I can have one subscript, two subscripts, three subscripts, and I can also have pointers. I don't have to have just array subscripts. I can have indirection. And I can have as many lines of code as I want. And so how do I abstract that in a similar way so I can say something about code that looks that general? What I'm going to say is that each inner loop index is associated with a tuple of integers, you know, I1, I2 up to ik. I'm going to be iterating over some subset of k tuples of integers. It doesn't have to be a nice brick. It can be an arbitrary sparse thing. And all I have to know about all this messy code is what do the subscripts look like. And all I'm going to insist upon is that there's some linear functions. They can be arbitrary linear functions of the loop indices. You know, and then I can have indirection. I don't care about that. But this guy, I1 plus 2I3 minus I7, that's going to be, you know, one linear function. And this guy is, you know, a list of linear functions. That's still linear. That's all I need to know. And these are projections, if you like. They take this tuple of integers and they do this linear projection onto something smaller. So all I need to know about this program is this list of projections. And then everything else I can write down. So, oops. So here is what the general statement is. And where does the linear program come from? So this is a theorem which goes back to some famous mathematicians from a long time ago. If you've ever had a class in functional analysis, you may have heard of Holder's inequality. So that's why his name is on there. And there have been some recent generalizations, but I'll tell you what the most recent generalization is. So here's the linear program, which says, please, first I'll tell you what the linear constraints are. Then I'll tell you what the linear program is. So here's a bunch of variables in my linear program, my constraints. And the constraint says, for all subgroups of k tuples of integers, so if you've had group theory, what's a subgroup? It's a subset of zk where you can add things arbitrarily and you stay inside the subgroup. And a subgroup has something called a rank. It's like a dimension of a vector space. And so this thing here is a linear constraint. This is an integer, those are integers, and this tells me that these s's have to satisfy a set of linear constraints. And I have one of them for every subgroup of zk. So let's suppose that, you know, so that's a set of linear constraints. So the theorem says that given a program that I just described with all of those array references described by these projections, then what I do is I choose all of these numbers to minimize their sum subject to these linear constraints. That's the linear program. So this is, you know, a linear constraint, all the s's, and that's the HBL linear program. So let's suppose I can solve that linear program. Then the theorem says that the number of words moved, no matter how you organize the code, is lower bounded by the number of loop iterations, no matter how many there are, divided by the fast memory size to the exponent, the magic solution of the linear program minus 1. Okay, and where does this come from? It depends on a recent result in very pure mathematics by a colleague, Mike Christ, here in the math department, Terry Tao at UCLA, and a bunch of other mathematicians in the UK. And so when they did this, they weren't thinking about computer science at all. This is very much a result in functional analysis and group theory, but it's exactly what we needed to say very general things about computer science. So let me just talk about, given this lower bound, can we attain it? So, I mean, this is a bit hairy, so maybe I should say a few more words about what this means. So the first question is, can I even write down this linear program, right? So what the heck is it? So let me come back to this. So H is a subgroup. The rank is like a dimension. So you can think of this as like a vector space, and this is the dimension of a vector space. It's almost the same idea. And so each of these, and this is a projection of a vector space, so it's a smaller vector space. So this is just a smaller dimension. So each of these things is an integer that could go anywhere from 0 up to k, because they're all subsets of zk. So all of these are integers between 0 and k. So I have to write down this inequality for every subgroup of zk. How many subgroups are there? There's an infinite number of subgroups. So this is why it's a question of, can I even write it down? So it turns out, though, that since all the coefficients here are integers in some bounded range, there's still only a finite number of possible different subgroups, possible sets of integers. So this really is a linear program, right? If you're a pure mathematician, you write it down in this infinite way, but it's still a linear program. There's still only a finite number of possibilities. Okay, so the first thing we said is, can we write down this linear program? And the first theorem we got here was bad news. It turns out that writing down all the inequalities that you could possibly get is equivalent to something called Hilbert's 10th problem over the rational numbers. Now, some people, you may know, Hilbert's 10th problem is a famous problem in pure mathematics. Hilbert stated it about a century ago. He stated it the following way. Suppose somebody hands you a polynomial with integer coefficients. Can you decide whether it has an integer solution? That's the original statement of his theorem. And back in the 1960s, people proved that was undecidable. There is no algorithm to actually decide that. Given an arbitrary polynomial with integer coefficients, you cannot write down an algorithm to decide if it has an integer solution. And that was proved by someone named Maciejewicz, but it was based on earlier work here at Berkeley by Julia Robinson. So that's Hilbert's 10th problem over the integers. Now, not the rational numbers, but the integers. Now, there's another version of Hilbert's problem, which is if somebody hands you a polynomial with real coefficients, does it have a real solution? That's a different question, and that one is actually something called Tarski decidable. And Tarski was another Berkeley professor back in the 1940s. So the rational numbers are in between the reals and the integers, and it's been an open question for 40 years. Nobody knows if this is decidable or not. So we were kind of stuck there for a while. But then, with some more work, there's good news. There's actually a subset of the linear constraints you can write down that provably has the same solution. So we can actually write down a finite set of linear constraints that does have the same answer, and so we can write down the linear program. And to actually implement this algorithm, which is decidable, means there is an algorithm. There's a paper, we have a paper that describes it, but it doesn't actually exist yet. I mean, nobody's coded it, so that's work to be done. Okay, so then the next question is, and this is the case that I showed you, all those special cases like matrix multiply and N-Body. If your projections, if your subscripts are particularly simple, if you're just allowed to pick subsets of the loop indices like ij and ik and stuff like that, then it's easy to write down explicitly, and the linear program was just those capital delta matrices full of zeros and ones, and they were just totally easy to write down. So that's the case where we know as much as we do. So let me now just assume we're in this best case where everything is really simple code, and I don't have I plus j minus 3k as subscripts, and ask, is it attainable? So the first thing is it obviously depends on something called the dependencies between one loop iteration and the next. So matrix multiply is the simplest. All I'm doing is adding stuff up. It doesn't matter what order I do it in. I can do it in any order I like, and addition is perfectly happy with that. It's associative. But if I had not addition, but something more complicated and messy and nonlinear, I might not be able to reorder the inner loops and block it the way I wanted to. So let me just assume that it's, that I don't have that problem. That it's like matrix multiply, that I'm just adding stuff, or there's no dependencies or whatever. Then the theorem says, here is how I'm going to write down the optimal algorithm. And it's not the linear program that came out of the theorem that I just showed you. It's the dual of the linear program. So if you've studied linear programming, every linear program has another one, which is kind of like the transpose. It's called the dual. And the dual is the one that tells me the optimal block sizes. So in that special case, when all the subscripts are just subsets of the indices like ij or whatever, then what I do is I take the linear program that came out of the theory, the HBL linear program, and I take its dual. So that just means that instead of, I just sort of, it's a transpose basically. Then the solution of this linear program tells me all the tile sizes, tells me how to do all the blocks. And so, and that's where all the three examples I gave you at the beginning came from matrix multiply and for N-Body and for sort of that random weird code that I showed you. Okay. So, if you're a compiler person, this extends not just to subscripts of indices, you can do more general stuff. But and it's an open question to make it work for completely general code. So this is ongoing work. We're trying to, one thing to do is we've proven it's decidable to write down the lower bound, but it hasn't been coded. It's not clear how expensive it is, so that's work to be done. So we'd like to actually, if somebody hands you code, sort of develop the compiler technology to automatically write down this linear program and figure out what the lower bound is. Because in principle, once we've figured out all this theory, it should all just go into compilers. In fact, we've been talking to people in the compiler community who would like to put this into, automate this stuff so that, you don't have to be, know all this theory in order to optimize your code. Your compiler will do it for you. And so that's sort of an ongoing process because there's a lot of, educating one another and all this kind of technology to make it all work. So another thing that we did in the matrix multiply work that I talked about before was we had this property called perfect scaling, that when you double the number of processors, I said, and you used all their memory, you could go twice as fast, everything scaled perfectly. That turns out to be true for these algorithms too, that if you double the number of processors and use all the memory that comes with, they scale perfectly. You go exactly twice as fast. Everything, all the costs go down by a factor of 2. And the really hard, interesting open problem is if you hand me some arbitrary messy code with arbitrary subscripts, I plus 3j minus 4k, anything you like, can I attain the lower bound? I think that's the biggest, interesting, hard mathematical open problem here. So, are there any questions about that? Was just sort of a tour of where all that theory goes. So generalizing, linear algebra and N-Body into other things.
What happens if the hard question gets answered?
So let me, so the question was, what happens if, you can bring the mic anyway. So the question is, what happens if the hard question gets answered? It's at least one PhD thesis. So, so I think that this will impact the way all compilers get built. At least that's my hope.
So the point is, if we can answer it affirmatively, or in the negative, that we can actually attain every lower bound, then it's a lot more reasonable to put it in compilers.
Well, the affirmative answer would be, say, please put it in compilers. But even the special case where the subscripts are just subsets of the loop indices is already, common enough that it's worth putting in compilers. The other thing is that even if we, so the point is, let's suppose that we just put the lower bounds into compilers. The compilers already have automatic blocking of loops. They just don't have a way to pick the block sizes very well. So if we could provide a lower bound, that would give them a success metric. They could say, well, let me just search. Maybe there's not a magic formula for their optimal block sizes, but let me just try a whole bunch of ones, compare it to the lower bound, and then they could say, oh, I'm done. I've attained the lower bound. I can stop searching. So there are several possible things that could happen. Okay. So I think that's a good place to stop.